double integrals in polar coordinates. So here's some familiar formulas. So in shifting from the xy to r theta, so in the Cartesian plane, in Cartesian coordinates, we have x and y. And so that's just like this, x and y. And in polar coordinates, we have r and theta. So r would be this length right here, and theta would be this angle. So for a particular point right here. Okay, so that would be, the coordinates at that point would be r theta. And the coordinates of that point here would be x, y, where x is this distance and y is this distance here. Okay, so that's the idea right there. Now, when you're dealing with polar coordinates, okay, so let me try to give you an idea of what's happening here. So remember, in Cartesian coordinates, we have these little rectangles, and so the area of a rectangle would be the area would be dx dy, right? Basically, so the dA right there. Okay, but in polar coordinates, what you're dealing with is something like this. So you have, let's say this is the origin right here. And they said this is your little area right here. But this right here is your dr. But this right here is r d theta. Okay, so this length right here, from here to here, is approximately r d theta. It depends on the radius. So if you move, like for example, if you move this radius, if this rectangle gets moved further this way, then this is going to increase in length. Likewise, if it's moved that way, or conversely, if it's moved back this way, okay, and you have the same dr right here. The same distance. This part here is going to be less though. Okay. So this blue part is going to be less if you're, so the blue part depends on the radius as well. Okay, so that means that when you do this integrals in polar coordinates, when you switch from, in particular when you switch from rectangular to polar coordinates, or even when you're just going to do something in polar coordinates, it's your dA is all that. Is r, dr, d theta. It's the product of those three. Okay, and here is a typical. This is right here is typical of what you're going to be setting up. Okay, so because x is r cosine theta and y is r sine theta, you replace the x and y by those, r cosine theta and r sine theta. And then, but then you have to make this r dr d theta. And one possibility would be where you have r being between h1 of theta and h2 of theta. Okay, so like, so just to give you an idea, let's suppose that you had something right here. This is, we'll call this r equals h1 of theta. And then you have another thing up here, and that's r equals h2 of theta. And you're integrating over this region right here. Then your r limits, your dr limit's going to be h1 theta to h2 of theta. And your theta is going to go from whatever this angle is to whatever to that angle. So alpha to beta. Okay, so that's just a rough idea of what's going on. Got to remember that's r dr d theta. So let's look at the first one. Evaluate by changing the polar coordinates. You got 2x minus y dA Okay, R is the region in the first quadrant enclosed by the circle, and the lines x equals 0 and y equals x. Okay, so here's the circle. What's the radius of this circle? Haha. Dang. This is not such a great circle. I guess it's round, but I didn't put it in the right spot. So its radius is 2, okay? And then you have x equals 0, that would be this right here. And then you have y equals x, and that would be right here. So we're looking at this region here. How can we describe that? And this region is actually what we call a polar rectangle. And so you might be like, what? This is not a rectangle, this is a wedge. It's a slice of pie, it's a slice of pizza, right? A slice of pizza is not a rectangle. Well, it's a polar rectangle now, right? That's what we call a polar rectangle because you can describe it with just 4 numbers here. Okay, so what does R go from? So if we just take a sample strip right here, what's the value of R when you're right here? That's just going to be 0. And as you go up here, what's the value of R over here? That's going to be 2. Okay, and then theta, what's this angle here? If that's y equals x, what's this angle? Dang, I think everyone's not paying attention. Okay, that's okay. That's pi over 4. And this angle here is pi over 2, all the way up there. Okay, so that's what we call a polar rectangle. Okay, so the integral is going to be, you change all the x's get changed to r cosine theta, and all the y's get changed to r sine theta. And then the dA gets changed to r dr d theta. Okay, so r goes from 0 to 2, theta goes from pi over 4 to pi over 2. Okay, and oh my goodness, this is nasty. You're integrating in R first, so that's going to be.
It would be R squared, wouldn't it? R squared minus R squared.
Yeah. Okay. So hold on a second. I don't know where that 2 came from. I'm sorry. Oh yeah, I gotta distribute the R's in, right? Let me do that right here, okay? Get rid of that. Because I'm not gonna have enough space otherwise. Okay, so this is gonna be 2r cubed over 3 cosine theta minus r cubed over 3 sine theta. That's integrating. And then I'm gonna r equals 0 to r equals 2. So 0 to 2 on the r. So plugging a 2 in, we get 16 right here. And 8/3. And now it's theta's turn to be integrated. Integral of cosine is sine. And the integral of sine is negative cosine. Okay, so plugging in the upper limit, we get 16/3. Sine of pi over 2 is 1, and then plus 18/3 times 0. So cosine of pi over 2 is 0, so that's 0. And then we have the lower limit, which is 16/3. Okay, so sine, so let me make a note right here. So sine of pi over 4 and cosine of pi over 4 are both
1/2, or no, root 2 over 3.
root 2 over 2. They're both root 2 over 2, okay? So that means we have 16 root 2 over 2, which can be 8 root 2 over 3 for this one. And this one's going to be 4 root 2 over 3. Wait, I'm confused. Oh, yeah. Okay, so this is 16/3. I'm on the right track. What am I thinking? Minus 12 root 2 over 3. So that's 16/3 minus 4 root 2.
That's the final answer?
Yep. Did you guys get it right? Kind of tricksy. Okay, ready to go to the next problem?
Yeah, that was right. Yeah.
Yes. Okay, so number 2, evaluate this integral here, where D is the region in the first quadrant that lies between these two circles. Now, if you take this one right here, you can take the 2x over here. And rearrange it like that. So you have it equals 0. But then if you add a 1 here and a 1 there, then you get x minus 1 squared plus y squared equals 1. Okay, so this is a circle of radius 1 whose center is at 1, 0. Okay, so if you graph these, this is the circle of the radius 2. This time I'm going to be more smart about it and put these down so I know where to go. There we go. That's a little better. Oh man. Okay, and then I was going to do it in purple. Oh well. I can still do it in purple. Okay, and then this one right here is the center's right there, so it's going to be like that. Ooh, this looks cool. They got big circle and then a little circle. So it looks like some creature's head with one eye open. Look at that. Okay, so hold on. D is the region in the first quadrant that lies between the circles. What? So D is actually this region right here. What the? Okay, so that's D. Okay, and I didn't draw this as good as I could. Let me draw this a little bit. There we go. Okay, this is kind of interesting. If you go, if you start from the origin here and you go out, you're going to intersect this circle, and then you're going to take a little ray there. You can do that in any direction, even if you do it this way. And even like the straight up is going to be just this right here. But if you're just a little bit this way, you're going to intersect the circle. You're going to be inside this blue circle first, and then you're going to pop out and go up there. Okay, so any ray from the origin out to this boundary, it's going to, if you do this, these rays are going to get covered everywhere. So this integral, okay, so the x is, so what do we change the x to? You guys remember?
No.
Okay, let me go back to the first page and show you guys. This is it right here.
Oh, right. R cosine theta.
And this is what you change y to. Y is r sine theta.
Hey, wasn't that Z though? Never mind.
Okay, so this is r cosine theta. Okay. What do you change dA to?
It's not the sine, is it? Our sine theta? That's y, right?
No. It's this right here.
Oh, dr d theta?
Yeah, so remember that dA is r dr d theta. Okay, remember this is the area right here. It depends on r also. The further out on the away you are, then the larger the dA is going to be. Okay. So this is r dr d theta. Okay, now the upper limit's going to be 2, because this right here, this part of the circle, or this whole circle, is basically r equals 2. Okay, this outer circle, the equation is r equals 2. Okay, this inner circle, this right here, this blue one, the left-hand side is r squared, right? And the right-hand side is 2r cosine theta. Okay, that's r squared. This is 2r cosine theta. Okay, so if you see this equation, what do you have the urge to do?
To change it.
What? Do you not have an urge to divide by r?
Yes, divide by r.
Okay, so that's okay. So this equation of this part of the circle, in fact the whole circle, is this, r equals cosine theta. So this lower limit is r equals 2 cosine theta. And that's what's going to go right here. 2 cosine theta is going to be the lower limit. And so what would the limits on the theta be? Okay, so pointing directly this way is 0, and pointing straight up is pi over 2. Okay, so that's what that's gonna be. Okay. So this is basically r squared cosine theta. So you take the integral with r, you get r cubed over 3, r cubed cosine theta over 3. And that's going to be evaluated from r equals 2 cosine theta to 2. Okay, so that's 0 to pi over 2 of 8/3 cosine theta. That's why I'm putting a 2 in right here. So 2 cubed is 8. Minus, and then I put the lower limit in, and this is where it gets nasty, because I'm going to get 8 cosine, what the heck? Well, cosine to the 4th of theta over 3 d theta. Okay, so it's okay if you use like Wolfram Alpha or something. What was that other thing that we guys used? Simplot or something?
Brotherhurst,
Yes.
won't it be like if you input all in, gonna be cosine squared, or am I getting it? Like
Well, I'm
input
putting
all.
this in for a cubed, r
Oh,
cubed.
it's the
So I'm
second
cubing
one.
this.
Oh, sorry.
So that's cubed. This is cosine. This is going to give me cosine cubed. So it's 8. So 2 cubed is 8, and then cosine cubed is cosine cubed times another cosine. So that's cosine to the 4th.
Okay. Sorry.
No problem. Okay, so now it's just integrating this thing, and this is not supposed to be about integration. You can use something to help you with these integrals on the homework, and I'll try to make it so the exam integrals work out okay. That's basically what the answer is. 8/3 minus pi over 2 is what we get in the end. The 8/3 comes from here, because you integrate, that's going to be sine. The sine of pi over 2 is 1, and the minus sine is 0, 0. So that one gives you 8/3. This one is pi, it basically gives you pi over 2 in the end. Okay, great. So that's number 2. So number 3, use a double integral to find the area of one loop of the rose. Whoa, roses. Wow. One loop of a rose. Okay, so r equals 3 cosine 3 theta. So essentially, you know that cosine of 0 is 1, right? And then cosine of pi over 2 is 0. So what's going to happen is if you set 3 theta equal to pi over 2, you get pi over 6. So essentially what's going to happen is when your angle is 0, then the 3 theta is going to be 0, so that means you get 3, right? And when the angle is pi over 6, it's going to be back to 0. Okay? And then the cosine is an even function, so you're actually going to have a part over here as well. But then these are the same. So we only have to go from, we can double it and go from 0 to pi over 6 on the theta, and we'll be fine. And r is going to go from 0 all the way up to this point right here, from 0 to 3 cosine of 3 theta. Okay, so that's the integral right there. That's what you get when you set it up. Okay, integrating in r, you get what?
You get r squared over r over 2.
Good. And these 2's are going to cancel, so that's great. This gives you cosine squared of 3 theta. Boo. No, 3 cosine squared. What the? That's 9. So you get 9 cosine squared of 3 theta, d theta. Okay, integrating that one. Again, it's cosine squared, so ouch. The double angle formula.
Missed that formula. So fun.
Yeah. Okay, so if you put a pi over 6 in here, whoa, yep. Whoa, that just goes away. Wait. Oh, that's interesting.
That's why I missed it. It's so easy. Things just disappear.
So you get basically 9/12 times 6 times pi over 6. Plus 0 minus 0 plus 0. So that's, oh, 9 over 4 is, I guess I should have reduced that to 3 over 4. Okay, so 3 pi over 4.
Yeah, that works.
You make the change like that. So this is the key points. So the key points are, just to refresh your memory, is those substitutions there, and then dA gets replaced by R dr d theta because of this right here. Okay, so those are the keys to that. So let's go ahead and look at this problem here. So you want the volume below this cone and above this ring. Okay, the cone is going to look, this cone is going to look something like this. But it keeps on going up forever. I don't know what that does. And then the ring here is going to be this. So if we go 1, and then if that's 2, then you have an inner circle and an outer circle, and the ring is going to be this part inside here. Okay, so if you can imagine, this is the x-axis, that's the y-axis. Imagine the z coming straight out at us, and imagine this thing coming straight out at us. Okay, so we kind of want to know, so what it's going to look like is you have a cone like this, and then you have this ring here, and you want to know this area, okay, under the cone, right? So this area, this solid, not an area, the solid, right here. Okay, so the volume is going to be the area, the integral over the region. If we call this region R, the integral over the region of the height, which is z, times the area, the dA. Okay. So in this case, the height is the square root of x squared plus y squared, but we're going to use polar coordinates. So in polar coordinates, what's z? What's this in polar coordinates?
Wouldn't that be cosine, r cosine squared plus
Yes.
r sine squared?
Yes. Yes, exactly. Square rooted, and that simplifies down to r. Okay, because cosine squared plus sine squared is 1, and then so you just get r, the square root of r squared, which is r. So great. So you have r, so that's your z. And what does your dA become? What did I just say your dA should be?
Oh shoot, it's up on the other page. I forgot what it is.
Oh well, okay, it's r dr d theta.
I remember that.
Yeah, everybody knows that. Okay, so let's see here. So now we need limits on r. And r is going to go from, this is radius 1 and this is 2. So r is just going to go from 1 to 2. And then theta is going to go from 0 to 2 pi. Okay, so theta, it goes all the way around, it's all the way around 360 degrees or 2 pi radians all the way around the circle. Okay. And r goes from, I guess this also could be thought of as r squared is between 0 and 4, which means r is between, I'm sorry, 1 and 4. R is between 1 and 2, so 1 to 2. Okay, so here we have r squared. So we integrate that. That's r cubed over 3 from 1 to 2. And that's r equals 1 to r equals 2. And that looks like 8 minus 1, so 7 thirds d theta. There's no thetas in here, so that means that that integral is just going to be the 2 pi minus 0, which is 2 pi. Okay, so 14 pi over 3. It'll be the answer to this one. Okay, let's go to number 5. Use polar coordinates to find the volume of the solid above the cone and below the sphere. Okay, so this is the same cone as the previous problem. but you want it, but this time you have a sphere. Okay, so if you think of it, you can think of it this way. Well, So you have that cone there, and then you have a sphere on top of it. So if you're looking at, if you're just like looking at it 2 dimensions, then it's going to be like that. So it's kind of like, the sphere is kind of like just a little bit of ice cream up there. Ooh. And so this right here, this radius, this is, wait a minute. Okay, so what it's going to be is all this stuff inside of the cone. Okay, so maybe you just packed in a whole bunch of ice cream and then you've flattened it with like with the sphere above. Okay, so this equation right here is z equals the square root of x squared plus y squared. The sphere is going to be the outer one. So again, we're going to set up the integral over here. We know that the dA part is r dr d theta.
dr d theta.
Yes, that's your dA. Okay, now what we need to do is we need to find we need to change everything to polar coordinates, okay? So this cone inside is,
It's the same as the one above, right?
yeah, z equals r. Okay, so that's z equals r right there. Okay, the sphere, okay, the sphere is going to be if you solve for z squared, you have z squared is 1 minus r squared. Dang, I don't know why I'm confused about this. Okay, so anyways, z is the square root of 1 minus r squared, okay? Okay, that's for the sphere. Okay, now, so what happens is we have this, what we need to do is project this, think of this back down on the XY plane. Okay, so this is, so here's X, here's, this is Y, and then X comes out this way. And then kind of think about what is the projection down here gonna look like. okay? And that's going to be a circle. So if, so essentially, if this is part of the cone, the radius is 1, so that part of the cone is 1, right? If we drop that straight down from where the cone and the sphere intersect, this is where z is equal to dang, I don't know why I'm confused. This is, well, anyway, this is 1 over the square root of 1/2, and this is also square root of 1/2 there. Because okay, so anyways, what we need to do is take this value for any value in here, the height of the cone is going to be this. I mean, I'm sorry, the height of the sphere is this, and the height of the cone is going to be this. It's going to be r. Okay, so that's r. Okay, and then this goes from the r goes from 0, because this radius here is going to be root 2 over 2, or 1, or the square root of 1 over 2. Okay, so that goes from 0 to root 2 over 2. That's the r range. And then the theta goes all the way around, so from 0 to 2 pi. Okay, so this becomes, now here's a trick that you can use. So notice that there are no thetas. So if that's the case, then what you can do is this outer integral, and there's no thetas in here either, in the limits here. No thetas there or there. No thetas, no theta there. No thetas in all this. Okay, so if that's the case, then you're going to evaluate this integral here, and you're just going to get some number. Okay, it's going to completely resolve to a number. And then you're going to integrate that number from 0 to 2 pi. So that's just going to be 2 pi. Okay? So that gives you that 2 pi there. And then the inside part, if we carry the r in, we get r times 1 minus r squared to the 1/2 minus r squared dr. And then, so all of this, so in other words, all that and that resolves to just 2 pi right there. And all we have is just this integral in r. Okay, so if we integrate that one, this is -1/3, 1 minus r squared to the 3/2. So you raise that by 1, minus r cubed over 3, evaluated from 0 to
Root 2 over 2.
Yeah. Okay, and that simplifies, if you like plug all that stuff in, well, let's see, that's going to be 2 pi -1/3 times 1/2 to the 3/2 minus 1/3 times 1 over root 2 cubed plus 1/3. Okay, so that simplifies down to something like that. Hopefully that's the right answer. So try 2 pi times 1/3 minus 1/3√2. Okay, yeah, that looks like it works. So let's go to the next problem, number 6. Here we're supposed to evaluate the iterated integral by converting to polar coordinates. Okay, so what you first have to do is figure out what these things are. So this upper limit, y equals, well, the y values go from 0 to the square root of 2x minus x squared. Okay, so when you're looking at these kind of integrals, that's the first thing you should evaluate. Is this first this dy comes before the dx. So look at the dy, and then look at this interval here, and have y go between there, and kind of look and see what this is. And that's, if you square both sides, you get this. Okay, and then if you take this last piece, so this is y equals 0. That's pretty simple. If you take this piece here, though, you get this. But this x squared comes over to the other side, and everything goes to the other side. So you have x squared minus 2x plus y squared equals 0. But then if you add 1, you get this. So it's really that. So really, you're looking at this circle right here. Okay, the center is 1, the radius is 1. Okay, so that's 2, that's 0. So that's what you're looking at. But another way to evaluate this right here, another route that you could go is you could just bring just the x squared over. And then change it to polar coordinates. That's r squared, and this is 2r cosine theta. And then cancel the r, so r equals 2 cosine theta. Okay, so that's more useful for looking at it. I mean, it's good that we have the visual with this. We know that that's what it looks like at this point. And essentially, what this is telling us is that we're going from 0. So y is going from 0 to the square root of that. And then x is going from 0 to 2. So that means that this is the region that we're integrating over. This region right here. Okay, and this upper boundary right here of the circle, this is r equals 2 cosine theta. Okay, so that gives us an idea of how to integrate this if we go from 0 to 2 cosine theta. So that's r goes from 0 to 2 cosine theta, and that will, those different values will sweep out that area. And then if we let theta goes from 0 to pi over 2, then we'll sweep out the whole inside of the upper half of the circle here. Okay, and then this is just r, right? So that's 4 times r, and then we have, this all becomes r drd theta. Okay, so all that becomes all that, and then this becomes that. Okay, so we have 4r squared, and then when you integrate that, that's 4r cubed over 3, evaluated from r equals 0 to r equals 2 cosine theta. Okay, plugging the 2 in here, you end up with 32 cosine cubed of theta over 3 d theta. Okay, and I'm not going to get into the details of this, but this integral ends up, so just cosine cubed of theta that's interesting. Okay, so I just used the, I guess that's an integral that you can actually do. It's not that bad. Oh well, but using a computer will give you something really weird. So that gives me what, 32 times 8 over 12 times 3. So 12 and 3, 32. You plug a pi over 2 in here, that's going to give you 9. That gives you 9. This gives you -1. So 9 minus 1 is 8. And then everything else is the same. And then when you plug a 0 in, you get 0. So so let's see here. If we reduce that by 4, that becomes an 8, and that becomes a 3. So that's what, 64 over 9.